nucleophilic approach takes place. So the positive charge that is induced on this carbon atom due to the presence of this chlorine is making this nucleophile approach this carbon with the positive charge, which we consider as the nucleophilic substitution on a saturated carbon. Now, since this carbon atom, being the saturated one, can easily undergo the nucleophilic substitution to give the different product. Now, when it comes to some of the reactions that are related to this nucleophilic substitution, are being the treatment of this ethyl chloride with aqueous OH minus. That is, any alkali like KOH, calcium hydroxide dissolved in water, or even the moisturized Ag2O, which can be represented as silver hydroxide, can be taken as a reagent which will replace the chlorine with OH. That means if you are interested in converting the ethyl chloride into ethanol, the best reagent to obtain the maximum yield is always being aqueous base, that is aqueous KOH or aqueous calcium hydroxide. Now, when this ethyl chloride being a nucleophile, ammonia will attack on it by the loss of HCl. It's going to yield the primary amine, which in turn itself is a nucleophile. Hence, if I anticipate this primary amine again to attack on ethyl chloride, as we can see, this nitrogen along with the lone pair of electrons is attacking on the carbon to give you diethyl amine. Again, the loss of H and chlorine took place. And dear students, you can make out again that there is a susceptibility for the nucleophilic substitution on ethyl chloride to give 3-degree amine. So, this is a continuous nucleophilic substitution wherein we can anticipate the formation of a 3-degree amine starting with ammonia, which is happening through the formation of the primary, secondary and tertiary amines. It's a successive nucleophilic substitution, my dear students. You can see every time we are generating one more nucleophile which is making this molecule again to participate in the nucleophilic substitution if there is excess of ethyl chloride present. So, when the questions are asked, they may give you the mole ratio with which the substrate and the reagent are participating. If it is clearly mentioned that they are reacting only 1:1 mole ratio, you please leave the product here. Suppose if it is given for every 1 mole of ammonia, there are extra mole of ethyl chloride which are being used, the reaction may go till the formation of 3-degree amine, which will further react with ethyl chloride. There is a possibility, you can see here clearly, that the nitrogen atoms still have the lone pair of electrons, which has the tendency to attack on this compound to ultimately again forms the quaternary ammonium salt. You can see here there is absolutely no possibility of losing the HCl because there is no hydrogen that is present over here, so that HCl can be lost. So, one can anticipate here the formation of the quaternary ammonium salt. This is something like simple ammonium salt, where there is a positive charge on the nitrogen and the chlorine hangs around that nitrogen by virtue of the ionic bond. So, now this is of the kind of nucleophilic substitution reaction that are taking place on the ethyl chloride. As we could see that alcohols are generated, amines are generated. Now we will be seeing some interesting aspects related to this nucleophilic substitution reaction when we change the cation. Now let us move on to the other reactions related. Now when I see that if I want to obtain the cyanides, as one suggests that Cl minus is a nucleophile, as we had a freedom in the previous reaction of using KOH or silver hydroxide. Here, if you take that liberty and you carry out the nucleophilic substitution on this, you may end up at getting the different products. Now, I mean to say, suppose if I take potassium cyanide or sodium cyanide, or we can even take the calcium cyanide, the product obtained was found to be the ethyl cyanide or propane nitrile. Now, when the same reaction, I mean the formation of the cyanide is anticipated with the silver cyanide or mercury cyanide, I mean mercury is it present in its +1 oxidation state, hence it can be called as mercurous cyanide. The product found to be the isocyanide or isonitrile. Now let's analyze the basic reason that is associated with the formation of two different products when the similar kind of reagents has been used. Now when we get into the details of these particular reactions, we will see that the cyanide ion, that is Cn minus, has two nucleophilic centers. One is with respect to the carbon, the other with respect to the nitrogen. Such kind of nucleophiles are generally referred as ambidient or ambidentate nucleophiles, which have more than one donating center, but do not forget the fact that at a time only one center is going to donate the lone pair of electrons. Now when I carry out this reaction with the potassium as the counterpart to the cyanide, as we all know that this potassium has no interest in the chlorine whatsoever. What I mean to say, that the lattice energy of the K plus and Cl minus, or the lattice energy of potassium chloride being low, we can say that the nucleophile has got the ability or chance to attack only on the partial positive charge that is present on the carbon. That means here potassium absolutely takes no initiation in dragging out the chlorine. But when it comes to the silver ion, I mean the ions like silver or mercurous, as we know that silver chloride is a white precipitate, Hg2Cl2 is a white precipitate, I mean to say that the lattice energy of AgCl and mercurous chloride is very high, and this has huge tendency to abstract the chlorine atom. Thus, by forming the precipitates of AgCl or mercurous chloride quickly, as I just suggested, that these have a lot of tendency towards the halide ions. So now, which is producing the carbocation. Now this has a choice of attaching with the nitrogen, as we know that the full positive charge is usually referred as hard acid and full negative charge is referred as the hard base or the